We looked last time at one-dimensional collisions using conservation of momentum. But one-dimensional collisions are a bit limiting. I mean, really, how often do things crash in perfectly straight lines? So we want to now be able to build on that and extend our knowledge to collisions in 2 dimensions. And one interesting area is accident investigations. So the cars crash. You weren't there to see what happened, but now you have to go back and look at skid marks and where the cars are and where they started from, and try to reconstruct what the conditions were like before those cars collided. So we're going to start out with a very controlled experiment. These are hockey pucks on an air table. So a bunch of holes drilled in the table there, and air is coming up, and there's 2 pucks there. There's the white puck here. The black puck may be a little harder to see. But this one is stationary, and this one's going to be colliding into it. So here it goes. That's it. Shall we see it again? Okay, one puck comes in and it has some momentum before the collision, and after the collision there's 2 pucks moving. So we'll play that again, but I'll kind of highlight what happens. This is where the puck started, this is when it collided, and then so this puck went from here to here. After it collided, it went from here to there. This puck was initially stopped, and after the collision it went from there to there. So here we go. All right, so I was very careful when I made this movie to make sure that the time that elapsed before the collision was the same amount of time after they collided. So this distance along the screen here, because it has the same time, will be able to give me the velocity before and after. So we want to see if the total momentum before the collision in this 2-dimensional collision equals the total momentum after the collision. Well, we have vectors here. This vector can represent the momentum of that one puck. So the momentum of that one puck is the total momentum before the collision. After the collision, well, this had momentum and this had momentum. Okay, so this was the momentum of that one after, and this was the momentum of this one after. And because these are vectors, you can add those vectors head to tail. So this after plus this after really does equal the same thing as the momentum before. I should say that these pucks have the same mass. That's why I can get away with just using the velocity for its momentum. There's another way we can do it. We can take that one momentum and break it up into components. So that momentum before has a component in the vertical direction and a component in the horizontal direction. This one has a component to the right, horizontal, and a component up, vertical. This one has a component to the left and a component up. So here we just took the overall momentum of the pucks and saw that before was the same thing as the total after. Well, let's do it now in terms of the components. This is the total momentum in the vertical direction before. So that's momentum in the y direction initially. Afterwards, this component over here now is the momentum in the y direction finally for that red puck. And then we also had this momentum in the y direction finally for that white puck, or the red outline, I should say. So this was before, and the 2 added together looks like they really do equal the same thing before and combined after. We'll do the same thing in the x direction. So this component in the x direction was the momentum in the x direction initially. After the collision, we had this with momentum and that little piece with momentum. So this was the momentum of the red outline after, and you can see we have a little bit more afterwards than before. Well, we don't actually, because we haven't added in this momentum. It was in the opposite direction. So we add those head to tail, and the resultant after is going to be the same as the total before. Momentum was conserved in both the x direction and the y direction. So let's apply that to accident investigations. Now, we are going to do this in a very controlled, maybe oversimplified way here, but it gives you an idea of what is involved in it. And then as you bring in more and more variables, it gets more and more complicated. But right now we're just looking at momentum. So here's this car stopped at the stop sign, and looking both ways, it seems to be clear. So there the car goes, and then this car comes out of nowhere, collides into it. They crash into each other, and we'll say that their bumpers link so that it is an inelastic collision, and they skid off to the left like this. Okay, so there's skid marks all over the road. Well, let's look at that in terms of conservation of momentum. Now, these two cars don't have the same mass, but this orange car had momentum in the y direction before the collision. The yellow car had momentum in the horizontal direction before. After they collided, the two combined masses moved off with this momentum. What we really want to do is we really want to figure out how fast was this car going. Because clearly, if this car had a stop sign and this one didn't, this car would be at fault if there weren't mitigating factors. For example, if this car had excessive speed, well, then this driver may not be as at fault if this car was racing or something. No wonder he didn't see him. He came from a mile away. So let's just kind of pare it down to just what we're trying to see here. We really want to figure out this velocity here. We know the mass of the orange car, we know the mass of the yellow car, and we know the combined masses of both cars. It's just added together. That's the total mass of both cars. Now, we remember when we were doing conservation of energy, we did an example where you could measure the length of skid marks and determine how fast that car was going when it first slid. And that was the work, the change in the kinetic energy would equal the work done. So let's say we did that, and we found that these two cars together, because of the skid marks, must have been traveling 10.4 meters per second right after they collided. And then as they skidded to a stop, that kinetic energy was transformed into something else because of the work done by the skid marks, the friction. So I know how fast those two cars are going because of the skid marks, and I know the mass of those two cars. So mass times velocity would equal the momentum of those two cars combined. So we have 35,439 kilogram meters per second of momentum from those two cars after the collision. Well, that should have been the total momentum before the collision as well, because momentum is conserved. Before equals after. And if momentum is a vector, and it is, we have momentum off in this direction. We can break that up into a component that's horizontal and vertical. And if you see police officers out there at a scene, they're measuring the length of the skid marks, and they're measuring the angles that the skid marks were at. Because if I know the momentum of those two cars and that angle, I can use the hypotenuse of that and the cosine of that angle. So the hypotenuse of that triangle multiplied by the cosine of the angle would give the component of that momentum that was in this direction. So I've got 29,721 kilogram meters per second to the left. I could do the same thing for this car. I'm not going to bother because we already know this car would have been at fault. We do know that they stopped at the stop sign. There must have been a video of it somewhere. Okay, but this component of the momentum is in the left direction, and this car didn't have any momentum in the left direction. So this component here of the two cars moving like this must have been equal to the momentum of the yellow car before the collision. And the component up like this must have been the component like that, of that one. So the momentum of this car is mass times velocity. We know how much momentum it should have had because we know what it was after. It should have been the same thing before. We know its mass. The only thing we don't know is its velocity. So divide both sides by 1900 and we figure out that that car must have been traveling 15.64 meters per second. Well, let's do a little unit conversion here. We got to convert the meters into miles and the seconds into hours. So 1 mile is the same thing as 1,609 meters. Meters on top, meters on bottom, cancel. Seconds on the bottom, seconds on the top, cancel. There's 3,600 seconds in an hour. So if I just take that, multiplied by that, divided by that, I get 35 miles per hour is how fast that car was going. Okay, the speed limit was 30. Wouldn't consider that excessive speed. So even though it was a race car, and maybe that person had lots of tickets and posted on social media that they like to drive fast, the evidence says they weren't driving that fast prior to the collision. So no mitigating circumstances. This driver's at fault. Now, when we did one-dimensional motion, we gave you an example of where momentum was conserved, but kinetic energy was not. And so the two cars collided and they stopped. All that kinetic energy was lost. The reason was momentum is a vector quantity. Momentum to the right and momentum to the left can add together to give you 0. But kinetic energy is not a vector quantity. So just this had some kinetic energy and that had some kinetic energy before the collision. After the collision, they didn't have any at all. So kinetic energy was not conserved. All right, let's do that with these hockey pucks now. We know that momentum should be conserved, but we want to see if kinetic energy is also conserved. So mass and velocity initially, we just had the one puck before. Afterwards, we had the two pucks, the mass and velocity of one, the mass and the velocity of the other. Similarly, with kinetic energy, 1/2 mass times velocity squared would be the kinetic energy of the one puck, and the kinetic energy of the one puck after added to this one after. Now remember, momentum is a vector quantity, so we do have to consider direction here. Kinetic energy is not a vector quantity, so we just take the kinetic energy and add it to the kinetic energy and see if it was the same before and after. We don't consider direction. This is kind of a special case, is where both of these pucks have the same mass. So if the mass of the one puck and the mass of the other puck have the same, it's the same mass all the way through and it cancels. And for the kinetic energy, we have a 1/2 in every term. And again, if the mass is the same in every term, both the 1/2 and the mass would cancel out of every term. So this equation simplifies to that the vector quantity of the initial velocity and the vector quantity for the final velocity added to the initial before equals after. Kinetic energy is just going to be proportional to the velocity squared. Okay, so if momentum is mass times velocity and we cancel out the mass, the momentum is going to be proportional. This is the symbol for proportional. Momentum is going to be proportional to the velocity. And since kinetic energy is 1/2 mass times velocity squared, if we cancel out the 1/2 and the mass, then kinetic energy is going to be proportional to the velocity squared. Here it was equal to 1/2 mass times velocity squared. So if I had the one hockey puck coming off in that direction like this before, and after there was a puck that went off like this, and after there was a puck that went off like this, we can see that momentum was conserved because these are vector quantities. This momentum in this direction added head to tail. The total momentum after was the same as what it was before. Now remember, the momentum here is proportional to the velocity. So if this one represents the velocity, that side squared, the velocity squared, is going to be proportional to the kinetic energy. So this side squared would be proportional to the initial kinetic energy. And this side squared would be proportional to the kinetic energy. And that side squared was equal to the proportional to the kinetic energy. So if the velocity squared before equals the velocity squared after plus this velocity squared after, like I have right here, then kinetic energy would have also been conserved. And you might recognize that diagram from math class when we were talking about Pythagorean's theorem, that if one term squared plus the other term squared equals the hypotenuse squared, these are the legs, if that's true, then that must have been a right angle. Okay, so back to this special case scenario here. If these two pucks have the same mass and momentum and kinetic energy are both conserved, the one puck comes in, this puck and that puck will bounce off each other at right angles to each other. And if they bounce off at right angles, then both momentum and kinetic energy were conserved. Okay, well, let's look at the one puck came in, and here, very different from this case. So instead of this puck going right off to the right and this one going up, the one puck bounced off at this angle and the other puck bounced off at that angle. Momentum was conserved. This momentum after added to this momentum after, head to tail, was the same thing as what it was before. So that does show that the momentum was conserved. But if you take that velocity and square it, that's the kinetic energy, same thing as what it was in this case. But here, this velocity squared, proportional to its kinetic energy afterwards, this is a smaller square than this. And this is going to be a smaller square than that. So even though momentum was conserved before and after, the total kinetic energy after would have been less than what it was before. Here, they were equal to what it was before. So if they come off at different angles like that, the total kinetic energy before was not equal to the total kinetic energy after. Kinetic energy was not conserved. Energy was conserved, but kinetic energy is just one form of energy. Maybe some of the kinetic energy was transformed into heat or sound, things like that. All right, let's see how well kinetic energy did in this collision. So this was just what we had before, and I'm just showing you a rectangle here, so that's a right angle. And we see that the pucks did not go off quite at a right angle to each other. So momentum was conserved, but kinetic energy we lost just a little bit. If you wanted to find out how much kinetic energy you lost, you would take 1/2 mass times velocity squared, add it algebraically, not vectorially. So you just add the numbers, 1/2 mass times velocity squared plus 1/2 mass times velocity squared, and you would have found that those two kinetic energies added together would be a little bit less than the kinetic energy of this puck before. Okay, and here we can see that they weren't quite at right angles either. All right, if you want to practice this, there is a link in the description to this video for a PDF that you can print off. And what I did is I videotaped it and then I played this back frame by frame. So we hit pause and then we advance one frame and then we see it here. And then we advance another frame and then we see it there. And we advance frame by frame. They collide and then we advance a frame. We now see this puck has moved to here. This puck has now moved to there. But we want to analyze that. We want to see if momentum was really conserved and how much kinetic energy was lost. So momentum is mass times velocity, and velocity is distance divided by time. Now we're going to do something funny here. We usually always want to stick with MKS units, meters, kilograms, and seconds. And we could absolutely put a meter stick on the Airtable that we're videotaping and scale up the size on our video to the actual size of the Airtable. We could find that scale. And we could find the mass of the puck in grams and convert it to kilograms. Okay, and we could find the time off the video as well. We're going to simplify all that. I'm going to measure the distance on my piece of paper in centimeters. Okay, so I don't have to scale it up to how far that puck actually went on the Airtable. We're just going to measure how far that puck went on our paper. So from the center of one puck to the center of the other puck would be the change in position. Okay, so we're going to measure the change in position, or the distance it went, in centimeters. We're going to measure the time. Now in slow motion, a video can make 32 frames per second, or I think 256 frames per second if it's really high speed slow motion. But we're just going to advance it frame by frame. So we're going to measure the time in frames. We hit pause here, and then we advanced right there, but that's only one frame of time. We could convert that to actual seconds, excuse me, but we're not going to bother doing that because it will all still be just proportional. So the velocity of this puck is the distance that it went divided by the time. And even though we see 5 pucks here, this time in between is just 4 frames. So we're going to measure the velocity in centimeters per frame, not meters per second. Okay, so over here, we're going to measure the velocity in centimeters per frame. And again, we could measure the mass of the puck in grams, convert it to kilograms, but we're just going to say this puck has a mass of, we're going to make up a new unit called pucks, and it's just one puck. So what are we going to measure momentum in? Well, it's going to be mass times velocity. Momentum would be measured in puck centimeters per frame. It's supposed to make things easier. It really is. It might tend to confuse. I'm sorry. Okay, momentum is mass times velocity, and velocity is a change in position over time. So this one puck came in, collided, that puck went off in this direction, and this puck, which was initially stationary, went off in that direction. And we're going to draw on our piece of paper, and we're going to measure, and we're going to see if momentum really was conserved. So if I measure from center to center here, I got about 13.21 centimeters, plus or minus 0.05 centimeters, and then 4 frames. So that distance divided by that time would be this velocity, and if I take mass times velocity, I get this momentum. That's how much momentum that puck had in our crazy units before the collision. And then we would do the same thing for here and there. Okay. But then we're going to draw in, these are going to be labels. We're going to draw labels. I kind of just slapped an arrow in that direction, and here and there, there, and there. I wasn't careful to make sure that these are just straight perpendicular to the horizontal, because they're just going to be labels. I'm not going to measure what those are. I'm just going to calculate what the components are. And I need to know the angle. So I'm going to use a protractor here, get the vertex right there, and measure that angle as precisely as I can. And I found it was about 41.1 degrees, plus or minus about half of a degree. So knowing this hypotenuse here and this angle, I can calculate this horizontal component here by taking the hypotenuse times the cosine of the angle. So that's going to be how much momentum was in the x direction. And I get 2.49. One thing I have to be careful of is that that was momentum to the left. I have to realize that that was to the left, and left is the negative direction. So I got to drop in a negative there. Okay, and then let's think about Sig Figs for a second. This had 4 Sig Figs. That looks like it only has 1 Sig Fig, but it was counted out, exactly 4 frames. And so our answer can only have 4 Sig Figs. So this had 4 Sig Figs. Our angle only had 3 Sig Figs. So our momentum here in the x direction should only have 3 Sig Figs, the weakest link. All right, so that's how much momentum was in this direction before. We could find the momentum in the y direction by just taking the hypotenuse and multiplying by the sine of the angle. And this is how much momentum I get in the up direction. I leave that as positive because up is the positive direction. All right, so I found the horizontal and vertical components for this. When you do it on your piece of paper, you might get different numbers, so don't just rely on my work here. We're going to do the same thing for those two, but be careful particularly with this one. A lot of students make mistakes here, where the distance the puck went is from the center of this puck to the center of there. So I would measure that distance in centimeters, and we have 1, 2, 3, 4 frames. Even though my line goes all the way down to my horizontal axis here, I measure from the center to the center to find the distance. I needed to draw that line all the way down to the x-axis there when I use my protractor, because I have to put the protractor at the vertex of that angle. So distance goes from here to there, not from here to there. Okay? All right. Now, you can print off this piece of paper and you can put your answers here and turn it into a teacher, or just look at it and be satisfied yourself. Or I do have a spreadsheet. It's also a link in the description to this video. So you can type in your answers here and the cells will turn green if your answers are within some tolerance. One last example I want to go through, and I want to just make absolutely certain that you do not need to know this example. This is second semester college physics or AP Physics 2, but I just want to introduce you to this idea that this is representing a photon of light. It is both a particle and a wave. It's interesting that photons have no mass, but they do have momentum. Photons have no mass, but they do have momentum. Photons have no mass. All of the mass that photons have is in the form of energy through the equation E equals mc squared. So if this photon comes in and collides with an electron, that photon of light, which has no mass, can actually knock that electron off. And so it's going to go boom like this. Okay? Now, the momentum of that photon is calculated with Planck's constant divided by its wavelengths. Don't worry about that right now. But if some of the momentum of the photon was given to an electron off in this direction, well, the photon that came off in this direction is going to have a little less momentum, because this momentum plus that momentum has to equal that one. So what happens is the wavelength gets a little bigger to make the momentum a little smaller. If you didn't like that example, don't worry about it. We'll stick with just standard momentum in collisions in 2 dimensions. It is conserved in both the x direction and the y direction. That's all I have.